Today we're going to look at electricity. Previously we looked at static electricity, in which case the charges would accumulate until they couldn't hold on to that area anymore, they couldn't be contained, and then they would jump. With electricity, we're looking more at a continuous flow of charges through a conductor, and that conductor has to be attached to some type of closed loop. If the charges are all at what we consider to be the same potential, then those charges will not in fact flow. So for electricity to occur, we need these constantly flowing charges to move through a closed loop, and it has to have a potential difference, or a difference in the amount of potential energy available to get those charges to want to move at any one point. So let's break this sentence down into a couple of pieces. The first part that we're going to look at is this idea of electric potential difference. Another name for electric potential difference is voltage. So we're measuring the voltage that something has. Voltage is effectively how much force, or the push, that we have making our particles want to move. So voltage could be described as the push from an area of high potential to an area of low potential in that closed loop. And voltage is similar to the idea of if I had a pipe that was connected to some amount of water, then that pipe is going to allow for a certain amount of water to want to get pushed across. If I have a lot, or a very high amount of water in my pool or tub up here, then I'm going to experience a high push across through that pipe wanting to come out the end. If I had only a small amount of water, so as I get near the end of that tub of water, still within the same pipe, I've got less push. So as something begins to empty, maybe that water wouldn't spurt up as much. When I have that higher pressure, I get more of a push through that water pipe. Similarly, voltage can be kind of viewed as that pressure, that push. So voltage would be similar to the pressure experienced in a water pipe. Now also in this sentence for describing electricity, we described electrons flowing. So electrons flowing is going to relate to something that we call current. Current in the equation is going to be notated by the letter I. And current is the flow of electrons, the flow of electrons from an area where we have excess electrons, so from a negative area to a positive area. That's what we typically define current to be. Now, we see some confusion when we talk about current for the fact that current is, we're talking about flowing electrons, but in terms of day-to-day or normal everyday life, when we try to measure the current, we're actually measuring what we call conventional current to be. And conventional current is what we now view as the convention, or as the norm. When we first started trying to talk about and measure current in the early days, we didn't quite have this understanding of a negative charge versus a positive charge. So we viewed everything as moving and something that made sense to the common man. So conventional current actually runs opposite of the actual realistic statutes. So conventional current would be the flow of a charge from positive to negative. So we're essentially saying here that protons are the things that are flowing. Now, we now know that protons are not the parts that are moving, that it's electrons that are moving. But because this was the first, or kind of the initial way that we measured, it's become kind of the norm, the normal description. But that's why it's generally prefaced as conventional current. So when we talk about current, most of the time people are talking about conventional current, which actually runs backwards from positive to negative. So it's a little bit of a false idea, but that's what we have as our standards. Now, everybody's probably heard a little bit about current and voltage. One of the important things to know about the two is that voltage itself is not typically the something that is going to be super deadly. I can touch high voltage things as long as they have low current without getting too much damage or having any issues. If you think about the Van de Graaff that we discussed earlier in one of our sessions, the Van de Graaff puts out high amounts of voltage, but very, very low amounts of current, and as a result is not going to be deadly or dangerous in any way. It's the idea of I could have a very, very hot spark, but if I was only touched by one spark very, very quickly, it wouldn't do a whole lot to me. With current, current has the ability to be deadly because we have this constantly flowing charges, so those charges always running through you can really start to build up and damage our cells pretty quickly. So only a small amount of current can be very detrimental, whereas a high amount of voltage is not so bad. So I mentioned that current in the equation is typically notated by the letter I. The units for current are going to be amperes, also known as amps for short. So amps or amperes for current. On the voltage side, our units are going to be, like you guessed, the volt, notated as a capital V. Now if we come back for a second and think about our little water line picture here, the pressure that was in that water, the amount of water that we had above our pipe represented our voltage. The actual water itself flowing through the pipe at any one point, that's going to represent our current. Now something that affects both that is going to connect the current and the voltage is what we call resistance. So resistance is the letter R in an equation, and just to get out of the way, the units for resistance are going to be the ohm, notated by the omega symbol. So resistance is going to be what causes or what restricts the flow of those charges through our pipe or through our wire. So what do I mean by that? If we think about our pipe, if we considered a wide pipe versus a very narrow pipe, if I have a very wide pipe and then it gets very narrow, when I get down here, I'm going to tend to see that I have higher amounts of pressure building up. So where we have this increase of resistance, we're going to also typically see an increase in our pressure or our voltage. At the same time, if I think about the water molecules or particles flowing through that pipe, where a lot of them can flow through over in this wider section, only a couple are going to be able to squeeze through at any one time in the smaller section, which kind of also helps us to see that as our resistance increase, we get less flow of those charges, so less current. So as far as resistance goes, things that are going to have a large impact on resistance, one of the biggest one being thickness of the wire. So if I have a higher gauge wire, where it's a thicker wire and I can have more charges in that same space, then I'm going to be able to get more charges across, more current, and I won't need as much pressure or as much energy potential to push those charges across, so less voltage. Other things that can affect resistance include the length of the wire. So if I think about having a longer hose or a longer wire, I'm going to need more pressure to get everything to go all the way through it, as well as the temperature of those wires. Hotter wires are also going to be methods that we are increasing the resistance. So to connect all these ideas together, we have something that we call Ohm's law. Ohm's law states that the voltage is going to be directly proportional to the current and the resistance. And with a little bit of algebra, I can see that my current would be, again, directly proportional to my voltage and inversely proportional to my resistance. Meaning that as our voltage goes up, our current would go up if our resistance stays constant, or if our voltage stayed constant and our current goes up, our resistance would need to go down. So we have our relationships there. If we look at how resistance relates to voltage and current, same basic principles. As our voltage goes up, our resistance would also go up, assuming that our current stayed mostly constant. At the same time, if our current went up, our resistance would need to go down, and in this case, our voltage would be the constant. The final two equations that we would use a lot when talking about electricity is relating it to power as well as energy. So power, as we've already seen in previous units, power is the rate that we convert that energy. Because it's a rate, automatically we should recognize that the equation is going to involve time. So power can be viewed in two ways. In terms of the rate that we convert energy, we have the equation that energy is power times time. And as a normal everyday way that we see on our electric bills, we typically see this as being measured in kilowatt hours. So kilowatts for power, because we typically use a lot of power at any given time, and hours because most things aren't on for minutes or seconds, they're on for hours at a time. The last way that you can measure power relates back to our previous equation, where power can be viewed as current times the voltage. For those of you